The last complexity class I will cover here is named NP-hard, and it holds problems that are at least as hard as the NP-complete problems. But the NP-hard problems do not need to be decision problems, and they do not need to be verifiable in polynomial time. Some of them are, and these are the NP-complete problems, but some are not, and among those is the knapsack problem, where the objective is to find the largest possible value that fits in the knapsack. Remember from the previous clip that even though the runtime complexity of this problem seems polynomial, it's actually exponential if we use the input size in number of bits to express the complexity. Another example of an NP-hard problem is the so-called halting problem, which is a problem of deciding whether a computer program will ever stop or terminate provided a given input. As a last example, we have the traveling salesman problem. Given a number of cities, the problem is now to help a salesman to find the shortest route that covers all cities and ends in the city where it started. That was 3 examples of NP-hard problems, and they are all silly hard problems to solve. But now we have seen examples of problems that are in complexity class P, and we have seen NP-complete problems, as well as NP-hard problems. What about problems that are just in NP without being NP-complete or NP? Let me get rid of the problem titles and copy the complexity class diagram. It seems rather intuitive that just because a problem is in NP and thus can be verified in polynomial time, it doesn't mean that it also sits in P and therefore can be solved in polynomial time. Because solving seems harder than just verifying. Intuitively, there must therefore be problems in NP that are not in P, and thus NP must be larger than P. But whether that's actually the case or not is still unsolved. That is, nobody has yet been able to make a formal mathematical proof that P and NP are different, and neither has anyone been able to prove that the two are equal. An example of a problem that is in complexity class NP but is neither known to be NP-complete or NP is the so-called graph isomorphism problem. Notice that I said that it was not known to be NP-complete or NP. This means that no one has been able to prove that the problem is in any of these 2 complexity classes. If someone someday can prove that the problem is not NP-complete and that it's not NP, then we know that P is different from NP, because we then have an example of a problem that is in the space between these 2, and therefore they can't overlap completely. If P and NP shows up to be equal, then all the NP-complete problems will also be solvable in polynomial time. And this means that all the 3 complexity classes P, NP, and NP-complete problems will cover the same set of problems. This will be huge. There's a lot of NP-complete problems, and there has been an enormous amount of research on many of them. However, to this date, no one has been able to solve them in polynomial time. So imagine if the apparently very hard problems that are NP-complete suddenly showed up to be solvable in polynomial time. I'm not the only one that is amazed by this unsolved question of whether P and NP are actually identical or not. In fact, the P equals NP question is one of the 7 millennium problems defined by the Clay Mathematics Institute, and there's even a prize of $1 million to the first person that either proves or disproves that P equals NP. Currently, however, more than 100 attempts to create such a proof have been registered on the so-called P versus NP page, so it's definitely not a trivial thing to solve. But if you by any chance is a genius and can either prove or disprove that P equals NP, then a whole lot of fame and $1 million is heading your way.